Okay. So this talk is possible future of EVM, and my name is Paweł, and I work in the Epsilon team at the Ethereum Foundation, and we mostly work on EVM design, specification, and implementation. We had some sidetrack trying to incorporate WebAssembly as an execution engine, but that's already gone, and we went back to improving EVM. So I want to present like three different topics that are kind of related in this talk. First one is to introduction to EOF, EVM Object Format. Then do some overview about control flow inside EVM and how can we relate that to other like intermediate representations and how can we improve that. And finally, I will talk about code validation of the deployed contracts. So starting with EOF, this is the term maybe some of you have heard of. We kind of started presenting that, I think, over a year ago. And this is like more structured object format from EVM. So to understand why do we want it, we need to kind of describe the current situation with EVM. So one of the rules that are still like viewable on the original wiki coming from early days of Ethereum is that we want EVM to be simple as a thing to implement, as a thing to reason how it works. But yeah, quoting my colleague, I think we overdone it a bit. So it's really simple in the way that it will just take any garbage code and will execute that byte by byte. And if it spots that something is wrong, it will abort at this point. So there is no like to say if the given code does something useful and like is properly structured, and will actually end up in like to have proper contract on blockchain. And that comes with some overhead. So you can deploy any bytes and say that's my code and that's fine. But then when you execute that, you need to actually do a lot of checks to make sure like this makes sense for EVM. So first of all, you actually need to check if the EVM progresses, the interpreter progresses to the next instruction. It actually has to check if this instruction if the instruction is there actually in the memory buffer it got. Because like the code can end suddenly in like some arbitrary point. So every time you actually loop in interpreter, it actually checks if it doesn't overflow the memory buffer it got. And similar checks are done for other things. So you need to check if for EVM stack underflow, you need to check for EVM stack overflow. And finally, you need to calculate the gas code of instruction. That can be like basic constant, or it can be some complex formula to do that. And after all of that, you can actually do some work that the instruction is supposed to do. And like for our EVM1 implementation of EVM, that comes from some overhead. And I think that's kind of like lower estimate how bad it is. So even checking like if we are looping over existing memory cost like about 5% on the benchmarks we tried. And if you disable some other checks, you get like some additional like 7% of different things. So why is this EOF related to that? So this is this is a container for a bytecode, so it actually specifies some parts of it. But what is most important, it is required to validate the EOF is correct before you actually deploy the code on the blockchain. So we end up in the situation when all the code that is deployed and is in the EOF format is pre-validated at deploy time. And the EIP that describes that, the basics of that is the one on the slides, 3540. So like giving some example how it looks like, I won't like describe all of the details what it is, but it's mostly binary format with some bytes meaningful to EVM. So it has like basic structure of prefix. It has some section headers and then the contents of these sections. So like to like introduce some of the things that are here. So we have some 2 magic bytes that actually will inform the EVM that this is the EOF format, and has like, so it changes how the EVM behaves if it spots that. We have also the version byte that we'll be able to use to change the specification on EOF, and then having some incompatible changes. And in the section header, we describe what kind of section the header describes and the size of the section. And then like the sections follows. And where the validation is happening is before we actually are able to deploy new contract to blockchain. So the runtime code is something you want to actually store in the blockchain, and this is on some given address. And this is the contract you want to use later. So when you have the runtime code, there's additional validation step that will check that if it's conformant to the EOF spec. And if it's not, we just throw it away, and then the creation fails. If it's fine, we can deploy that to Ethereum state. That's not the full picture, because you have to get the runtime code from somewhere. And in Ethereum, it's not like a single step to get it. It's actually like a 2-phase creation. So when there's create transaction or there's create instruction, it will actually have init code there. So in the transaction or in the create instructions. And this init code role is to actually produce the runtime code. Usually this means that we'll just copy the code from some other section, some other part of the bytecode, and return it as our runtime code. But because we have this ephemeral init code, we want to actually validate it for EOF compliance as well. So the EVM doesn't have to distinguish EOF code that has been validated from the EOF code that hasn't been validated. So this like validation process actually happens for init code as well, and after it's valid, this can be executed and processed for storage. And so what kind of validation we mean here? I mean, we can check that the basic structure on EOF has I like partly described. So let's say that's it's our current proposal is to, for example, make the code section in the EOF mandatory and have also like special data. It's not really special, but have like data section that is not executable. And that's optional because maybe not everyone wants to have some data in a contract. And if we zoom in on the code section, we can have some additional checks that will restrict what kind of code you can have. So, for example, you can prevent using opcode that doesn't have defined meaning. So you can't have like undefined instruction in your code, and you can require that the code actually ends with some terminating instruction. So it can be stop or anything that actually returns from the execution. The last one is actually something that helps with one of the checks I already said. So every time you loop the interpreter, you need to check if the instruction is actually like physically in the memory. With that, you have guarantees that you will find some terminating instruction from the interpreter loop. So actually, your loop doesn't have to check for existence of bytecode. And and this, like, if you like design it pretty well, then we can have some properties about coming from this validation. So for example, you can add new instructions. I mean, yeah, you can add new instructions. I could define new instructions for EVM later on. And that's safe because we know that nobody used this opcode in existing contracts ever. And similar, that enables the designing instructions differently. Currently, it's really difficult to introduce instruction that has immediate values because that's theoretically breaking change. And it's also really difficult to find examples statically if that will break any contracts. So that's like, there was some number of historical proposals to EVM that were rejected because they try to use immediate values of instructions. And now this is enabled with EOF. And we can also remove existing instructions. Even in the first version of EOF, we can remove something that we consider deprecated, like a call code instruction and maybe self-destruct. So if you want to know like more about EOF, I think that there are three sources I recommend. One is the EAP itself. Secondly, there's a like introduction article about that. And finally, we also recorded a PEEP and EEP session that talks about that. Yeah. So like secondly, I want to move to some other topic, is like how the control flows looks in EVM, and that is mostly about the jump instructions. So there are two instructions. There are two jump instructions in current EVM. One is unconditional. The second is conditional. Like the condition is not really important right now for this subject. But what is kind of interesting is that it takes the target when you want to jump to from the EVM stack, which makes it like what people call like dynamic jumps. So we don't know at the deploy time where the jump will go to. And like I think like better term would be direct and indirect jumps. That's what is used in other like sources. But well, the question is, can we improve that? And it can be shown like most of the targets of current deployed contracts are known during compilation, like during deploy time. So we don't really overuse that feature. There's only one thing that is important when you have some kind of function emulated in Solidity. When you return from that, you need to the return point is stored on the EVM stack. So what I did is try to compare like this situation with EVM with like some other like intermediate representations, which I'm mostly familiar with. And like the common situation is that there are like 4 different kinds of instructions that control allows are related to control flow. So there are direct and indirect jumps, and kind of like similar there are analogous instructions that relate to function calls. And like EVM situation is mostly this, right? We have this indirect jump, which it's generic enough so we can implement all of the others with it, but it comes with a cost that we might want to improve on. So the improvement we're kind of proposing is that introduce static jumps, which mean that the target of the jump is coming as the immediate value after the jump instruction. That wasn't really possible before. But yeah, with that, with this like EAP 4200, we can do that, and that proposes this one, and like and we also aiming to remove the existing dynamic jumps. That's not like the first step we'll do, but I think on the horizon we want to have that. And so that leaves us with the thing that we can't really implement functions in the contract because that requires dynamic jump at least. So to do that, we just want to have instructions that will actually implement function call natively. So it will be used to have native functions in contracts. And there's to fill up the table, there's also possibilities to extend it a bit. So have kind of version of indirect jump based on predefined offsets in the bytecode. That is more or less goes along with other intermediate representations where even though there's some selections of targets, you have at least predefined what the set of targets is per instruction. And kind of similarly, we can have indirect call, but question here is mostly that if that's useful for contracts, and the usefulness of that is at least questionable. So I mean, it's technically it's possible, but so far we're not confident that will provide real life usage. And finally, coming to the third part is how can kind of combine that and design the code validation in a way that we at least can eliminate the checks EVM has to perform, but also it should improve the readability of contracts. So you can it should be easy to audit and reason how the contracts work on the bytecode level. So this is kind of prototype we recently done, and it's it validates statically analyzes the code section in the way that it can detect misbehaviors. And this is inspired mostly by Java and WebAssembly. It's still homework for us to actually compare in details how the different procedures work in the different languages. And there are also proposals coming from other people, mostly Greg Colvin, that try to kind of work in the same direction. But because the procedure itself is not really complicated, we kind of just did naive first version, and then we'll try to compare the differences from other sources. And the terms that show up here is mostly type validation and abstract execution, but it simplifies a lot in the EVM context. So, if you talk about type of instruction, so all other typed intermediate representations. So mostly what you want to, how do you want to think about the type of instruction is kind of the function type. So it has some type of number of arguments of given type, and it outputs some results. But because EVM doesn't really have it actually have single type, let's say this way. So we can just ignore what primitive types are in the tuples. But what we care about is the number of inputs and number of outputs. And that's what we're going to analyze. So mostly the procedure goes starting with the first instruction, and instead of executing the instruction, it mostly operates on types. But in terms of EVM context, you mostly care about the number of the number of items you have on the stack. So the procedure tracks the stack height during this abstract execution. So it goes from instruction to instruction and records how the stack height will change. And in case you spot a place in your code that goes below 0, that means that will cause stack underflow. And you also want to track the maximum stack height. during this some code section analysis. And like special cases here are only jump instructions. Okay. So if you spot like unconditional jump, you just follow what it says to go to. And if you spot the conditional jump, then you kind of need to inspect both branches of that. And that's like a bit more complicated case. But mostly that's all about that. So the prototype is like still like in the draft phase internally, but it's not more than like 73 lines of Python code that does all of this. So if you're interested in detail how it works and like maybe you find a way to break it or find some interesting cases that the validation will not approve, or yeah, anything else. So yeah, please welcome. Go to the pull request we have. So coming back to like to the EVM design, like how the checks will evolve with that. So first of all, with this like basic code validation, we eliminate the first one that checks if the instruction exists at all during execution, and also this the stack height analysis gives you, allows you to eliminate the stack underflow, because that should never happen when you execute a section of code. However, the stack overflow cannot be like fully eliminated. That's why we record the maximum stack height the function can have. And then when you want to call a function, you need to just check if there is enough stack space and the current runtime context to be able to execute given function. So like it's not like fully eliminated, but it happens only when you have this special function call instructions. And yeah, it doesn't touch the gas calculation and all of that at all. So these checks will remain as they are. At least that's not the proposals that try to tune these. So like in summary, that's more or less my vision, like how can we evolve EVM, and I think like most my team members are kind of agree with that. So like mostly that's driven by EOF, EVM Object Format, where this way we get some nice properties about EVM execution. It's like code and data separation in bytecode, support for native functions in the bytecode where they are like occupied in different code sections, improved control flow, and yeah, and all of that should lower the execution overhead. Yeah, so that's all I had for now. And if there are questions, I'm happy to. I think we have like 2 more minutes. And also, if you're interested in working on something like that, we have some open positions at the team. So yeah, please welcome. I'm being invited to reach out. The best on the email address on the slide. Thank you.
So just to make sure I understand correctly, the stack height validation is going to be done by the VM when you deploy the bytecode?
So it's, well, like by VM implementation this way. So like by the client, right? Yeah. So you can, yeah.
So what's going to be the cost for it? Because if like an attacker crafts a contract for which computing the stack height is really costly, how do you prevent that?
So like we pay attention like what the complexity of the validation is. I mean, this is definitely like linear complexity, but there's like this one complicated case of conditional jump, which we need to explore 2 different branches. But we never actually validate more than we don't validate any instruction twice. So like
Okay.
we'll only visit like every instruction in the code once. That's for sure. And yeah, but like it's like kind of, so like the simple answer is like it's proportional to the code size, and we want to introduce the cost of that already before even EOF will be live, because that's already the case for current EVM. I don't think I have like a lot of time to go into details, but even now, when you have init code for creation, you need to do some analysis to find the valid jump destinations, and that's already proportional to the size. So we want to fix that before, actually.
Okay.
So like during deploy time, you will have additional cost proportional to the init code size, and deployed code size is kind of already done, right? Because there's like big cost of single byte deployment. So I think that's included somehow, because like it's like 100 times cheaper to do the analysis than like deployment cost. So I think you don't have to tune it.
Thanks.
Yeah, I think, sorry, I kind of...
Yeah, we are running out of time. Thank you.